Hello everyone, we are Group J. We are gonna introduce a paper which is named Improved Training of Wasserstein-GANs. This model can achieve the effect of imitating real pictures to generate highly similar pictures. We are gonna introduce in this order. To figure out the metric behind WGA and GP, we need to introduce the original model, GAN, first. GAN stands for Generative Adversarial Network. The basic idea is that, given a training set, this model learns to mimic any distribution of data. There are two main networks in the model. One is called the generator, the other one is the discriminator. The generator generates new data instances, while the discriminator tells apart fake data from true data. The whole process goes on like this. Firstly, the generator takes in random numbers and returns an image. Secondly, this generated image is fed into the discriminator alongside the stream of images taken from the actual dataset. Then the discriminator takes in both images and returns probabilities, a number between 0 and 1, with 1 representing a prediction of the generated image coming from the true dataset and 0 representing fake. The goal of the generator is to fool the discriminator, while the goal of the discriminator is to identify images coming from the generator as fake. Although GAN has shown great success in the realistic, there are still lots of problems in training due to the defect of the loss function, like non-convergence, mode collapse, diminished gradient, and so on. The most important problem is that the generator cannot cheat the discriminator. The loss function of the discriminator cannot give instruction on the training process. If the two distributions do not overlap at all, the generator generates pure errors for the discriminator, which will cause the generator to only try randomly. To solve this problem, the author modified the loss function. However, the new loss function will cause the generator to generate only the most correct data, without covering the entire distribution. That brings a new severe problem, that's lack of diversity.
WGN uses the Wasserstein distance, which is also called Earth mover distance. We can move some boxes to explain it. There are two boxes on rotation 4 and rotation 6 in the axis, which represents a distribution. We hope to move them to rotation 3 and rotation 7, which represents another distribution. We can find two methods to transporting them, as it is shown in the right picture. The cost of one moving action is the number of moved boxes times the moving distance. The total transport cost is the sum of all moving action, and the minimum transport cost is the Wasserstein distance. The Wasserstein distance between these two distributions is 2. For more complex distributions, we can also find the minimum cost to move a distribution to another, as it is shown in the picture. So, we can use Wasserstein distance to measure the difference between two distributions. The small Wasserstein distance means the two distributions are similar, and vice versa. Being different from the loss function used in the original GAN, even if the two distributions do not overlap, the Wasserstein distance can still smoothly reflect their distance. Unfortunately, this kind of optimization is not practical in many cases, certainly not in domains where GANs are usually used. In our example, we use a one-dimensional random variable. For many applications, like images in our demo, the input can easily have thousands of dimensions, so we can't calculate an exact Wasserstein distance. Fortunately, we can use a function to transport mass and use neural network to learn this function. But there is a limitation of the function which is called Lipschitz constraint. The author of WDAN used white clipping, which means limit the whites of the neural network in a certain region to meet the limitation. White clipping leads to two problems: difficult training and slow convergence. The improved WDAN, which is also called WDAN-GP, use another way to meet the Lipschitz constraint limitation and solve the problems above. The author of WDAN-GP verified by experiment that the parameters of the discriminator in WDAN, shown in the figure below, are almost concentrated on the maximum and minimum values, which means each node in the net is just a binary classifier, which limits the performance of WDAN. They use gradient penalty instead of white clipping to meet the limitation. It adds a gradient penalty function to the original loss function of WDAN. Instead of applying clipping, WDAN-GP penalizes the model if the gradient norm moves away from its target norm value 1. As it is shown in the picture, the numerator distribution on parameters is much more reasonable, and the discriminator can make full use of its own model fitting ability. The gradient penalty also solves another problem brought by white clipping. The performance of WDAN model is very sensitive to the length of clipping region, which is C in the picture. The gradient norm will become too big or small, which lead to slow convergence. The gradient penalty can keep the gradient smooth during the backward propagation without parameter tuning, which makes WDAN-GP very easy to train and get good results.
To compare the performance with other GAN, we borrow this matrix from the paper. Each row represents a generator and a discriminator design, and the column represents different loss functions. As we can see, the WGAN-GP version can perform well even under poor generator and discriminator design. Here, we provide a demo you can run in Colab. Let's go through a trial example. Maybe it will help you understand how to train a GAN and how to implement WGAN gradient penalty. Basically, there are 5 components for any GAN, namely prepare the data, define a generator and a discriminator, define loss functions, specify optimizers for them, and training. First, we import some library we will use, include TensorFlow. Also, we set the parameters we will use later. Then, we need a dataset. In this trial example, we simply sample some data from a distribution. After that, we specify generator and discriminator. They are just fully connected neural network. We define loss functions for generator and the discriminator here. Also, the optimizer for both of them. This project some utility function will help us to test and save the result. For the training part, GAN models needs to train 2 models, one for generator and one for discriminator. The training for generator is just normal gradient descent. But for discriminator, we implement the gradient penalty. Besides the gradient penalty, other part is just gradient descent. Now, we can start to train our model. It will show the image every 100 iterations. After the training, we can see it learned quite well. The green points are what our generator generates, and the orange ones are real data. The contour shows how the discriminator makes the decision. To see the power of WGAN-GP, we tried this model on different datasets. We first tried 2 datasets from internet. One is Celeb A, one is Animate. Without any change to neural network and the training procedure, the final results for both cases are good. Then, we use host dataset contributed by classmates and the Kingfisher data we collect. The results are not quite well, probably because of the quality of the dataset. That's all for our presentation. Thank you.